Yeah. Thanks for the introduction, the chance to speak. It's good to be here. Yeah. So just first a little bit on the setup. Um, so in this talk, M is going to be a closed Riemannian manifold. Maybe I should say it's going to be smooth since, there's been some interesting work on like scalar curvature and low regularity, perhaps, or probably even like there have been some talks in this seminar about that. So I'll just say, uh, in this talk, M is going to be a smooth Riemannian manifold. Um, and I should also say what scalar curvature is. So probably this has been defined in every single talk in the seminar here so far, but I'll just really quickly say what it is. So basically, if you wanted to summarize the curvature tensor of a Riemannian manifold at every point with just one number, the scalar curvature would probably be the number you choose. Um, and so one way to define it is just as the average of the sectional curvatures through all of the tangent two planes to whatever point you're looking at. Um, yeah, and up to, and people have different conventions for how it's scaled, but um, uh, yeah, with that, that's maybe the first definition of scalar curvature. And so how you think of it, like I don't know, the metric geometry, like geometric meaning, for what this is if you compare the volumes of metric balls at the point P you're looking at in your Riemannian manifold to just balls in Euclidean space of the same radius, uh, then to first order, they're going to be the same because Riemannian manifolds, when you zoom in, they look more and more like Euclidean space. But sort of the first interesting term you get in the Taylor expansion will be determined by the scalar curvature. And so if the scalar curvature is positive, that's telling you that volumes of small balls are smaller than balls of the same radius in Euclidean space. And similarly, if the scalar curvature is negative. Okay. Right. So, yeah, so first a couple words on just kind of the general philosophy for like what uh sorts of questions this talk is going to be about. Um, right, so in the setting of positive scalar curvature, a question that people are interested in and that's led to a lot of really great mathematics and still I guess there's ongoing work that's really great too. Um, is what sorts of constraints having a positive scalar curvature metric places on the topology of a smooth manifold, right? So that's a really like rich, interesting question. But in this talk, we're going to look at negative scalar curvature lower bounds rather than positive scalar curvature or non-negative scalar curvature. Um, and so for that, it's going to have to be a little different because, I mean, any given smooth manifold, at least if it's compact, I mean, you can always get it to have any given negative scalar curvature lower bound just by rescaling. So kind of from the start, you see that kind of the question is going to have to be a little different. And so yeah, kind of what sorts of questions we're going to look at in this talk are whether, given a scalar curvature lower bound that's negative, um, whether if you have that, and if you know something about the topology of the ambient manifold, then what kind of information that gives about the geometry of M, like what sorts of like can you estimate like different sorts of like metric geometry um, invariance associated to M if you know that you have a negative scalar curvature lower bound and there's some knowledge of the topology of M. And in practice, now, I mean, you'll kind of see a lot of examples of this, like the knowledge of the topology of M, it often means there's a canonical Riemannian metric, and that ends up being sort of um, the guide to the kinds of statements that you'd want to prove, where like whatever inequalities you're proving, the the canonical metric should be the I don't know, like the equality case or kind of the model case for that. Um, okay, so I'm gonna start by yeah, stating kind of like very general conjecture uh due to Gromov, right? So maybe the first, I mean, metric quantity you think to look at in this connection might be volume. Okay, and so that's what this conjecture is about. Um, and so what it's saying is that, I mean, if you have okay, a scalar curvature lower bound, and if you know something about the topology of M, namely that what's called its the simplicial norm of its fundamental class is non-zero, um, then what the conjecture is that you would be able to get a volume lower bound from that, right? So what it's saying is that um, I mean, if you have kind of having like a non-zero simplicial norm for your fundamental class is preventing you from being able to collapse your Riemannian manifold while keeping the scalar curvature lower bound, right? So if you collapse like the volume of your Riemannian manifold, then the scalar curvature has to be getting very negative somewhere. Okay. And so I'm not going to really say what the Gromov simplicial norm is, except so I'll just kind of I'll explain this with an example, right? So if M has a hyperbolic metric, if it has a constant curvature minus one metric, so I'll talk about hyperbolic manifolds a little more in a little while. Um, then the this quantity on the right side of the inequality is up to constants just the hyperbolic volume of M. Right. And so in general, if M has a negatively curved or a metric with negative sectional curvature, then this like Gromov simplicial norm of the fundamental class is going to be uh, Gromov-Thurston is going to be non-zero, and so you'll according to this conjecture, you should be able to get a volume lower bound. Um, okay. Any questions so far? Or, so, right. So yeah, I want to just give kind of a quick overview of what's known. Um, I think in the abstract of for this talk, I might have said something like in the negative scalar curvature lower bound setting, like not so much is known, and I think that's true in comparison to the positive scalar curvature or non-negative scalar curvature setting. But as I was preparing this talk, I realized there's actually a decent amount of work in this direction, and so yeah, so much work even that I'm probably going to forget to mention or neglect to mention like some yeah I mean work that's been done here. So sorry in advance if I do that. And also I should say that like in the setting of negative scalar curvature lower bounds, I mean there's different sorts of questions people ask too that are very interesting. So there's like a version of the positive mass theorem in this setting, and there's even like recent work by Brendel and Peak and Hung that is kind of about negative scalar curvature lower bounds. And so that's all very interesting, but it's a little different from what this talk is going to be about, where you really we're looking at kind of closed Riemannian manifolds, and we kind of want to like say things based on knowledge of like some topological feature of M. Okay, so right, so for this conjecture, so what's known about that in particular? Um, well, and so in dimension two, you can just check with the Gauss-Bonnet formula that it's true in like a very kind of sharp form actually, and so that's a yeah, simple exercise with the Gauss-Bonnet formula that you should do if you haven't worked this out yet. Um, the 3D case is harder and um, more interesting, and so we sort of only know the 3D case as a byproduct of Perelman's proof of geometrization. Yeah, and really this is like 99% due to Perelman, and I'm just writing Anderson's name because in the case that um, if M has like multiple components in this geometric decomposition, then Anderson kind of gave the argument. But really, this is mostly yeah, just Perelman's proof of geometrization. And so basically, in the three-dimensional case, the only way the simplicial norm here in the right side of the conjecture, inequality in the conjecture, the only way that can be non-negative or sorry, the only way that can be non-zero is if there's some hyperbolic piece, right? So it's kind of like this reduces basically to the case that M is a closed hyperbolic manifold or M as a hyperbolic metric. And in that case, turns out that yeah, Perlman's proof of geometrization using Ricci flow will yeah give this kind of like a sharp um, version of this conjecture as a byproduct. And then I should also mention in four dimensions, there's yeah some cases where this conjecture is known. For example, say like the product of two genus two surfaces. Um, say closed genus two surfaces, and so that's due to LeBron. And basically, if you have non-vanishing Seeberg-Witten invariance, then there's like a Bachner formula for the um, uh, yeah like Seeberg-Witten like harmonic spinners where scalar curvature comes out, and so kind of in 4D there's also there's like kind of some special thing that kind of tells you ends up kind of giving these sorts of uh, volume lower bounds as a byproduct. So the moral of the story is in maybe in low dimensions, there are just some kind of like special things that happen um, that kind of let us get this kind of know this conjecture true as a byproduct. But I would say like in general, very little is known here. Um, yeah, and I've basically told you all of the progress towards this conjecture, I guess, as it's written. Um, okay. But let me mention a couple related settings or like some progress towards the conjecture under some additional conditions. So um there's this thing called macroscopic scalar curvature, um, which what that is so if you remember from a couple slides ago, I gave you this interpretation of scalar curvature in terms of the volumes of small balls. And so the why this this way of thinking about scalar curvature is hard to use is that you don't actually know like how small you have to make R in order to like get this sort of I mean expansion for like the Taylor series to be true or whatever here. And so the idea with macroscopic scalar curvature is to say like say you knew about like balls with a fixed radius like that balls with fixed radius were not that large. That would be like a scalar curvature lower bound, right? So um, more precisely, it's like if you look at the universal cover, then you'd want to say that unit balls in the universal cover um, are not that large. Like there's some uniform bound on how large unit balls are in the universal cover. And so that's what macroscopic scalar curvature is. It was introduced by Larry Guth. And there's kind of a natural version of this the Gromov conjecture and the macroscopic scalar curvature setting. Yeah, and that's been pretty much, yeah, completely resolved by yeah, work by Larry Guth and also more recent work by Brown and Zauer. Yeah, and so this is macroscopic scalar curvature setting, which I guess you'll hear more about next week or the next talk, I guess, and this I think is about that. There's a lot of really interesting questions there, which I'm not going to talk about anymore in this talk, but pretty much any um, yeah, I mean, anything I talk about from now on, you could also ask whether there's a macroscopic scalar curvature version of it, and it's probably also interesting. Okay. Um, and I also mentioned work by Ma Wang Yuzhu and Ma Niu that is proving this conjecture, but or kind of things in the direction of this conjecture, but under some additional basically like bounded geometry assumptions. So stuff like in the universal cover, there's a uniform lower bound in the injectivity radius and stuff like that, where I think it's like meaningful progress towards this conjecture. Which yeah, so I would say that for the conjecture on the previous page. I mean, even kind of if you like add some assumptions, I think it's yeah, I mean the kind of in the most like general form, it's like seems like it's pretty much impossible to make any progress on, and so I think any sorts of progress under some additional assumptions is very interesting and kind of worth. Yeah. Okay. Great. So that's so much for volume, right? So that's kind of one of the um uh yeah, maybe the first geometric quantity that you'd want to look at. But what are some others? So you could look at the spectrum of the Laplacian, and there's work by, I guess, first Ono and then DeVoe uh, that is proving upper bounds for the bottom eigenvalue of the Laplacian um, uh, on just like L2 functions, the universal cover. Um, and so that's, yeah, I mean, a very yeah, nice inequality there, where the model case, it turns out, is if you're a hyperbolic manifold, then um, this will actually be an equality. So actually the bounds here are sharp. Um, and so yeah, I would say if you know about the Lorel theorem and the positive curvature, like positive scalar curvature lower bound setting, this Devon-Ono result is a little bit like a version of that, but in with a negative scalar curvature lower bound instead of a positive scalar curvature lower bound. Um, okay, so that's there's yeah, you can kind of say some things about the spectrum of Laplacian. Um, you could also look at try to like say things about the like how kind of lengths of sort of distinguished one-dimensional subobjects of your Riemannian manifold, like how that um, would be related to or controlled by a scalar curvature. And so you see right away, so even just looking at the case of hyperbolic surfaces, if you just look at one curve, right, maybe you'd want to control the length of that. Well, you can't actually do that because for a hyperbolic surface, it's always given any curve on a hyperbolic surface. You can always like collapse that curve. You can pinch the curve off while keeping uh, while kind of keeping the curvature equal to -1, right? So kind of it's well known like the like space of hyperbolic metrics on a genus bigger than one surface. It's the 6G minus 6 dimensional space where you can kind of you're able to just like any given simple closed curve, you can just sort of like collapse the length of that. Right. And so that tells you that if you just look at one curve, then you can't really hope to say anything. Um, but yeah, so really what uh, you have to do in the negative curvature setting is look at kind of like all of the non-contractible closed curves at once, right? And so this is, I guess, um, uh, something that people maybe first started to do in the context of dynamical systems and the study of in-also flows, right? And so, right, so there's this topological entropy quantity that um, I'm going to define now. That yeah, I mean it's coming from dynamical systems, but basically what this is it's just a measure of how many like how fast the number of geodesics, closed geodesics counted by length um, is growing. Okay, so it's the number of I counted the number of closed orbits of the geodesic flow. Okay, and so maybe should have said that M should have negative sectional curvature for this. Yeah, I would have written that if I was giving this talk on my iPad. But yeah, so you have this quantity that is basically it's just measuring like the rate of growth of the number of closed geodesics. So it's you can sort of think of like if you have just a model const like say, I don't know, hyperbolic or Einstein metric on your manifold, and you take some long closed geodesic in that metric that's kind of like almost uniformly distributed, and then if you then look at this metric G, um, then this quantity is sort of telling you whether like the length of that really long geodesic in the hyperbolic metric and the model metric is shorter or longer than what in this metric G than what it would be in the hyperbolic metric. And so that's kind of one way to think of what this quantity is measuring. Uh, just like how the lengths of kind of very long or large homotopy classes of loops, how they change from metric to metric. Um, yeah, and so I just have it on the next page too. right? And so it turns out this is computed by yeah, like the entropy of the geodesic flow and negative curvature. Um, yeah, Manning, that's basically due to Manning. Um, right. And so that's kind of a in the native curvature setting. Um, this is kind of something that it's common for people to look at. And so we're going to specialize to the case that M is hyperbolizable. The case that M has a constant curvature minus one hyperbolic metric, complete constant curvature minus one metric. All right, and so these are maybe the most natural class of closed negatively curved manifolds to look at, where you'd kind of hope to prove these sorts of statements um, relating negative scalar curvature lower bounds to like different features of the geometry. And so a key fact here um, is that the hyperbolic metric on a closed manifold, if there is one, is actually unique up to isometry. And so this is proved by Mostow. Um, and so yeah, that's why kind of in what follows will be justified in kind of speaking of the hyperbolic metric on a Riemannian manifold, because there's actually only one if you're finite volume. Um, okay, and so I'll say for other sorts of curvature conditions, uh, there's a pretty satisfying picture, and so for this next theorem, it's about Ricci curvature, right? So it's a that's yeah a stronger curvature condition than scalar curvature. Or Ricci curvature lower bound is a stronger condition than scalar curvature lower bound. Um, and I should say so. This next theorem is due to Katak, or different parts of it, I guess, kind of. So Katak did the two-dimensional case here, using like, the length area method. It's called, I guess, which is maybe goes back to Lovener or maybe earlier. I'm not sure. So in 2D, there's yeah, a really nice way to do this, just kind of using the uniformization theorem. But then in general, and I also say that in 2D, Ricci curvature is the same as scalar curvature. So like the 2D case of this is really it's scalar curvature, but in higher dimensions it'll be a stronger curvature condition. And so that's mostly I guess coming from Besson-Lowe, at least the second part of this theorem, and work by Manning. And I also should have said Bishop Gromov, but I forgot to write that in this theorem. But yeah, but um, what the theorem is saying is that if you're Ricci curvature tensor, which you think of as being kind of like a Laplacian of the Riemannian metric, like a nonlinear geometric version of the Laplacian of the Riemannian metric. Um, then what this theorem is saying is that the topological entropy of G um, is um, is at most that of the hyperbolic metric, and you have rigidity in the case of equality. So if you have equality here, then you actually have to be isometric to the hyperbolic metric. Right. So it's saying that Ricci curvature, at least, I mean that's able to sort of control length, um, kind of in at least in the sense of uh, controlling the growth rate of the number of closed geodesics counted by length. So that's the first part. And then also another kind of byproduct of this turns out is that you get a volume lower bound for M if you have this curvature condition. Okay, so yeah, so if the Ricci curvature is at least that of the hyperbolic metric, then you get this volume lower bound, right? So this is sort of like a sharp version of yeah, this like Gromov conjecture from before, but with Ricci curvature replacing scalar curvature. And in fact, yeah, for Ricci curvature lower bounds, I mean, Gromov originally proved this kind of a statement in that setting, right? So that's part of the motivation for this conjecture, I think. But then Besson-Lowe proved the sharp version for hyperbolic, real hyperbolic manifolds, and also I mean some other rank one locally symmetric spaces. Um, Okay, so that's for yeah, Ricci curvature lower bounds, and so that's a pretty um I mean yeah, satisfying theorem in that setting. Um what I'll say as a remark, and this is pretty recent, it's due to Cazares, Song, and Zhu, is that this is actually false if you replace Ricci curvature, the Ricci curvature lower bound with a scalar curvature lower bound. So the first inequality here actually won't be true with a scalar curvature lower bound and dimension greater than two. Um, and yeah, and so that's due to Cazares, Song, and Zhu. And so that's saying that I mean, yeah, scalar curvature turns out, I guess it's expected that scalar curvature lower bounds, like that's enough to control volume, um, kind of in the setting of hyperbolizable manifolds. But it turns out that it's not enough to control length, um, in this sense. Okay, and that was yeah recent work by Cazares, Song, and Zhu. Okay, any questions so far? Cool. All right, so okay, so in 3D, um, scalar curvature lower bounds, negative scalar curvature lower bounds can't aren't so good at controlling length. They can control volume by like this result by Perlman that I mentioned earlier. Um, the next question is what about area, right? And so in particular, you can ask like whether there could be any kind of analog of this previous theorem that I stated, but instead of closed geodesics, if you were to look at kind of at minimal surfaces, which are higher dimensional versions of geodesics. Um, right. And so yeah, and so this is kind of something that I think people haven't started to look at until fairly recently, and there's some good reasons for that. So for closed geodesics, on the one hand, they have a dynamical side to what they are, they're closed orbits of the geodesic flow. But on the other hand, there's a variational side to them. I mean, you can get them by just minimizing length in a homotopy class, or a non-trivial homotopy class of loop, right? And so in um, the setting of negative sectional curvature, these two perspectives come together in a really beautiful way. And so there's a really rich theory there. But for minimal surfaces, I would say um, they're much more variational objects than dynamical objects, um, in how they've been studied and really in how they are in a lot of ways. Um, but for kind of what I'm going to talk about now to kind of like make some of these analogies to closed geodesics work, we want to look at minimal surfaces from a dynamical perspective. And I would say, okay, this is fairly recent, but some of it goes back a little while. So I mean, Gromov has some papers from the like 1980s or early 1990s about foliated plateau problems, where he's sort of looking at minimal surfaces as part of a family in the same way as people would study geodesics as part of a family, kind of like in the geodesic flow perspective on them. And so I would say there's certainly precursors to this that are earlier, and I'll return actually to kind of some of this work by Gromov from a while ago. But what I would say is really what kind of lets or gets a lot of this stuff off the ground is work by Kahn and Markovich that's comparatively recent. And so I want to talk about that now. So M is going to be a closed hyperbolic three manifold. So yeah, for I guess the next part of this talk, or really the rest of this talk, we're going to look at the three-dimensional case. Um, and so we want to look at some class of minimal surfaces where there's a chance for um, there to be like a good analogy to closed geodesics, and some of the results from the previous slides. Okay, and so the idea is that we want to look at surfaces that are topologically essential, right? So in the setting of negative curvature, closed geodesics are always homotopically non-trivial, right? So we want some kind of like topological non-degeneracy condition. And so that's just like pi-1 injectivity condition, like the map on fundamental groups induced by inclusion has no kernel, is injective. Um, right? So we look at these these topologically essential surfaces. And we require in the hyperbolic metric that their principal curvatures be smaller in absolute value than epsilon. So we think of these surfaces we're looking at as being almost invariant under the geodesic flow, right? So the idea is like if there's any kind of hope for some dynamical perspective on um, minimal surfaces in hyperbolic manifolds, for example, then um, I mean, if that actually can work out, then the ones where you'd have the best hope for that would be the ones that kind of have like at least some connection to um, the geodesic flow, say. And so the ones we're looking at are going to be, yeah, these ones that are kind of like almost invariant under the geodesic flow. And even for these ones, I mean, in the hyperbolic metric, right, this is like these are kind of almost invariant under the geodesic flow. But if you look in some other Riemannian metric, that's probably not going to be the case. So even for these ones, maybe like at this stage, maybe it seems like it should maybe seem like a kind of a long shot to kind of expect an analogy to the geodesic flow and negative curvature to work. Okay, but then okay, so um, there's this theorem by Kahn and Markovich. So what they showed was that you can actually construct a lot of these surfaces, right? So you can find lots of closed, almost totally geodesic surfaces in any given closed hyperbolic three manifold, right? So this is a really big breakthrough, or it's a really beautiful application of dynamics to group theory, where they're sort of building these surfaces out of pairs of pans using like, mixing properties for the frame flow. Right. But for us, this is going to be kind of just like the input where, okay, these are sort of the natural sorts of minimal surfaces to look at. Um, and we're going to try to prove things about them in analogy to what's true for closed geodesics. Okay. And so the key fact here, due to like different proofs from a while ago, by now this is kind of a classic fact, but it's due to Sachs-Uhlenbeck and Shane Yao, which is that given any metric on M, you can minimize area in the homotopy class and get a minimal surface. Okay, and so I realize I haven't said what a minimal surface is, but for the purposes of this talk, you can think of minimal surfaces as just being like area minimizing representatives for non-trivial homotopy classes. Okay, and so this is um, analogous to the fact that given any um, homotopy class, non-trivial homotopy class of loop in a Riemannian manifold, a closed Riemannian manifold, you can minimize length and get a closed geodesic. And so this is like the minimal surface version of that, or higher dimensional version of that. Okay, and so having given some of the background here, can now define this like minimal surface entropy quantity. Um, Calling it entropy maybe is a little bit not quite the right term. Maybe it's more of like a relative entropy, but it's not such a big deal. But the idea is just to imitate the definition of the topological entropy kind of for counting closed geodesics, but instead of closed geodesics, you're going to be counting um, these Kahn-Markovich homotopy classes of surfaces by area. Um, yeah, and so it's a little bit of a different normalization here. So for one, it turns out that counting these by area, like the kind of they're going to be growing super exponentially. So A log A is really the thing you want to divide by, not just A. Um, and also we send epsilon 0, so that we're looking at kind of the ones we want to look at the ones kind of we want to look at surfaces that are becoming closer and closer to being totally geodesic. And so what this quantity is measuring is say you have, yeah, in the hyperbolic metric, you have some very large, almost totally geodesic surface. Um, then what this quantity is measuring is if you look at some other metric G, then whether the same homotopy class of surface would have larger or smaller area in this other metric. So that's kind of how you can sort of think of this quantity and the actual details of kind of, I mean, yeah, the definition here, I mean, is not so important, but yeah, this is kind of measuring the asymptotic growth rate of the Kahn-Markovich minimal surfaces counted by area. Okay. Um, and so the theorem about this that I want to state, just joint work with Andre Neves from maybe yeah, from a few years ago now, um, is that if M is, so it's a closed Riemann manifold with a hyperbolic metric, um, then if the scalar curvature is at least that of the hyperbolic metric, um, then we get an upper bound for this minimal surface entropy quantity. Um, and then you also have rigidity in the case of equality here. Okay, so it turns out that so scalar curvature, negative scalar curvature lower bounds in the setting could control volume, couldn't control length, but it can control areas of surfaces, at least kind of um, these sort of like almost totally geodesic surfaces. Okay, I should mention, I should say a couple comments. So first, I'm lying a little bit in the statement of this theorem, because there's actually this like modified version of the entropy that in general we have to look at. So the point is that we want to look at surfaces that are becoming uniformly distributed in the hyperbolic metric, and so if sometimes you can have these kind of Markovich surfaces that are like scarring along a closed totally geodesic surface. And if that happens, then it turns out that, as stated, this theorem is false. So really, you have to look at the modified minimal surface entropy, so it's called. So you look at like these surfaces that are becoming uniformly distributed. But for a generic closed hyperbolic three-manifold, this will be true. Um, so if there are no closed totally geodesic surfaces, then the theorem, as I've stated, is fine. But in general, I'm lying a little bit. But that's just a technical point. It's not a huge deal. Um, So another remark. So if M is finite volume but non-compact, right? So a lot of the easiest hyperbolic three manifolds to kind of like give examples of are in this category. So for example, like knot complements would be finite volume but not compact. So like the figure eight knot complement, for example. Um, like S3 minus the figure eight knot, that has a complete finite volume hyperbolic metric, but it's not compact, right? So this is an interesting class of, or I mean, maybe, I don't know, arguably the most interesting class of finite volume hyperbolic manifolds are non-compact. Um, uh, and this, an analog of the theorem that I just stated, but for these finite volume non-compact ones, was proved by Jiang and Vargas Piet. And you'll see kind of in the proof. So we're going to use Ricci flow. And the finite volume setting, there's some considerable technical difficulties if you sort of like uh, do a linearization analysis of the Ricci flow at the hyperbolic metric, if you're not compact. And so that's really what the difficulties that they have to deal with and what they're doing. Um, and then another remark. So a corollary of this was to answer a question that Gromov asked on kind of giving sharp lower bounds for something called the average area ratio under a scalar curvature lower bound. And so the average area ratio, I'm not going to say what it is, but you can think of it as being like an intrinsic version of this minimal surface entropy quantity, right? So this minimal surface entropy, it couldn't have been defined before Kahn-Markovich's work, right? So it's kind of using the existence of yeah, all of these essential surfaces inside your closed hyperbolic three manifold, or like it needs that to even be defined. But if you wanted to define a version of that that's kind of measuring the same thing geometrically, um, the same or at least a very similar thing geometrically, but without reference to specific surfaces in them, then there's this average area ratio quantity, which Gromov introduced actually like quite a while before all of this, like maybe in the or like circa 1990. Um, and then he proved originally this um, a non-sharp lower bound for this average area ratio quantity given a negative scalar curvature lower bound. Um, and so yeah, but what kind of what we're doing, we're able to prove a sharp lower bound. And it's interesting, like I think to prove that, like I think we really do need the existence of all these like closed minimal surfaces, at least for our proof. Um, Possibly there'd be a way to do this without reference to closed minimal surfaces, like in what we're doing. But yeah, we're kind of using these like hallmark surfaces to prove this. And so an idea, so like to give kind of so like, kind of the first difficulty here um is right. So given a scalar curvature lower bound, a negative scalar curvature lower bound, you do get area lower bounds for minimal surfaces, right? From the second variation formula. Okay, so this is maybe the argument for that. It's similar to how you would prove the fact that closed three-dimensional tori don't have PSE metrics. Is you'd find a minimal surface and you look at the second variation formula. Well, if you kind of do something similar here, then what you'll get is an area lower bound, but it actually won't be sharp. It won't be sharp. So if you just use the area lower bound from the second variation formula, then the bound you'd get here would be off by a factor of three, right? So the theorem we're stating like that you get like a bound that's off by a factor of three, it wouldn't be sharp, it'd be off by a factor of three. And so somehow, like in what we're doing, we need to be using kind of information of a more like global nature about the Riemannian manifold than what you would get from the second variation formula, which is sort of only seeing things kind of like at the minimal surface. Like we have to be kind of we need some kind of a tool of a more global nature than the second variation formula. And so the thing that we use is the Ricci flow of surgery. Okay, and so what I say is that it seems possible that kind of theorems like this could be true in higher dimensions. But of course, like Ricci flow, I mean, in higher dimensions, is that's not going to work, at least with what we know now. And so what I would say is that um, finding a way to prove this theorem without the Ricci flow would be great, right? It's a little bit of a crutch. Um, but yeah, but as it is now, I have like no idea, and I think it would be very interesting if someone could improve on the second variation formula in any way in this sort of setting without using the Ricci flow. Okay, but yeah, anyway, so we're using the normalized Ricci flow with surgery, and this is I guess it's following what Proman or I guess kind of the proof of the volume lower bound given a scalar curvature lower bound that is a byproduct of Proman's proof of the geometrization theorem. It's kind of I would say motivated by that or that's the ansatz. But there are going to be some additional difficulties here that don't arise in the case where you're just trying to control volume. Okay, so let me okay, it looks like okay, I still have a little bit of time. So let me give the idea, the proof of this, and then I'll talk about an application. That'll be the rest of the talk. So the idea is, so we run normalized Ricci flow with surgery. So the point is that so this kind of like it's like Ricci flow equation, which is a nonlinear heat equation where we evolve the metric by that. And after finitely many surgeries, we will be very close to the hyperbolic metric if we kind of make the time large enough, right? And so the idea is that the normalized Ricci flow surgery is going to take us back to the hyperbolic metric, right? So you see like the hyperbolic metric is going to be fixed by the normalized Ricci flow. So it's sort of set up that so that it's fixing the hyperbolic metric. The hyperbolic metric is a fixed point. Um, and the idea is we're going to keep track of how the relevant geometric quantities are evolving along the Ricci flow, and get a contradiction if the inequality we're trying to prove is violated at the end. So how is this going to work? So to give kind of a simplified model for how the argument's going to work, we can think of M as having a closed, totally geodesic surface that's very large. It's very large. Um, and so if the theorem we're trying to prove isn't true, right? So in general, M will not have a closed totally geodesic surface. So I'm just assuming that as like a toy case or as a way to kind of explain the argument um, in simplest possible terms. Um, so what's going on if the theorem we're proving is not true is that it turns out, so if the asymptotic growth rate of these asymptotically totally geodesic and hyperbolic metric, if the of these like Hallmark-rich minimal surfaces, if it's slower than what it is in the hyperbolic metric, then what that means is like, okay, if the growth rate is slower, that means they have to be larger, right? If you think about it for a second. And so what's going on here is kind of the thing we have to rule out is if the area of the homotopy class of this like say large totally geodesic surface and some other metric that has the scalar curvature lower bound, um, if that area is smaller than what would be in the hyperbolic metric, and that's sort of the thing we have to rule out. Okay, so that's if assume for contradiction that this sort of an inequality is true. Then what happens is that okay, if we look at the difference between um, the area of sigma in the hyperbolic metric and the area of sigma in the metric G, it turns out that the normalized Ricci flow surgery, I mean that's going to be preserving this kind of difference in the areas up to this exponential area term, exponential area term. And also the scalar curvature will be preserved under normalized Ricci flow surgery, it turns out. The scalar curvature lower bound will be. And so that's coming from like the maximum principle or the scalar curvature satisfying a parabolic equation. Right. And so what one and two do, these two observations, is they let us reduce to the case that we're very close to the hyperbolic metric. Okay. And from there, that's really the hard part. Okay. So the hard part is the argument in a small neighborhood of the hyperbolic metric. That's really where we have to do most of the work in the paper. And just to say a couple words about that. So what we do is we do just a linearization um, analysis of kind of like the convergence of the Ricci flow, the normalized Ricci flow back to the hyperbolic metric. And so for that, we're using work by Knopf and Young to do that. And so really it ends up being important for us the not just the precise exponential rate of convergence um, back to the hyperbolic metric, but also kind of like how it's converging back. So we have to actually kind of take the tangent vector we're converging back to the hyperbolic metric along by, which is the symmetric 2-0 tensor, satisfying some equations. And we also use the fact that sigma is very large, that we're looking at surfaces that are becoming almost uniformly distributed. And in order to say that, like to go from kind of like the area of sigma being large to saying that it's becoming almost uniformly distributed, we're using Ratner's theorem. So there's sort of a component to this that's also yeah, I mean that's from homogeneous dynamics too. That's going into this that I'm not really emphasizing as much. Yeah, and so that's kind of how the proof of this works. Okay. Uh, so that's yeah, so that's the proof of this theorem. Um, and in the remaining couple minutes I have here, I just want to talk a little bit about an application of this theorem that's kind of part of more recent work. Okay, any questions about anything? Uh,
I have some question because when you say surface, do you mean embedded or immersed? Because you say in homotopy class, so a priori it will be not embedded, but immersed.
yeah, very good. So not embedded. In fact, horribly not embedded. So yeah, so the sorts of surfaces we're looking at are
But
going to
once
be
the moment it's allowed on embedded, then you have to say simple or not, because you may have multiple of every surface. And under perturbation, this may be unstable. So each surface has lots and lots of exponentially many coverings of a given degree.
yeah. So
So
that's
how
okay.
you
That's
count them?
yeah. Right. So for this
It's much
okay,
more dramatic
yeah,
than
a
for
couple
geodesic
comments.
here.
Yeah. So right. So these the Calegari-Marques-Neves surfaces they're going to be intersecting themselves a lot. So they're becoming uniformly distributed, and so they're going to be intersecting themselves a lot. And then you're asking, okay, so how do we count them? How do we count them?
Yeah.
Um, yeah, and so as this like minimal surface entropy, like as it's set up now, we do count covers. We're actually counting covers of a fixed surface. That's something that's a little bit unsatisfying about the setup here, I would say. I would say so. Really, what we would want to do is we would want to count like surfaces within a commensurability class, not like a conjugacy. I mean, yeah, we would want to we'd want to have it be set up more like that so that we're not looking at covers of a fixed surface. But As it is now, we do look at covers of a fixed surface, which, as you're rightly observing, there's going to be a lot of covers of a fixed surface, and so that's like kind of factoring into the proofs in a way that isn't entirely satisfactory. I would say, yeah. But yeah, we're looking at just to summarize, we're looking at kind of specific minimal or specific homotopy class of surfaces. These Kahn-Markovich ones that are homotopic to almost totally geodesic surfaces in the hyperbolic metric, and so in general, they're going to be they're going to be intersecting themselves a lot. And also, there will not necessarily be a unique representative
But
in the
still,
homotopy class.
you said too many things. So when you
That's all right.
count them, you allow them to be as a surface non-simple, but being multiple. It's in
Uh,
your formula.
Sorry. Okay, I think I was confused about the word simple. So,
Simple
um,
being not multiple with another surface.
yeah, yeah. So we are,
Geometric multiple or just
yeah, yeah.
homotopy
So you're
multiple.
right. So,
There are two-way
and
multiple.
you're right. It's a good question. And how this is set up, we're counting non-simple ones. Um,
So you count
or not non-primitive,
all of them,
non-primitive.
all of them.
All of them, yeah, all of them, yeah. So
Okay.
that's I think it's basically this like measuring the same thing geometrically as if you didn't do that, but it's
But
certainly
because
it's
exponential factor.
unsatisfying. Yeah. What?
Exponential factor. You see, for closed geodesic, it's not so radical, yeah, because only but there are only very few
Yeah,
covering.
that's right.
Here
It's
it's
like linear. Yeah,
exponentially
yeah.
many.
You're
And
right.
so
You're
the
right.
entropy definition,
That's right. That's right.
they change the constant.
Yeah. Yeah, it's a big difference. I think, yeah, so the version of this without yeah, where you would just count like the simple ones you're saying or the primitive ones. I think this should also be true. The limitations for that are more on the Kahn-Markovich side where so Kahn-Markovich, they're able to produce like basically, I don't know, G to the G, I don't know, different commensurability classes of their surfaces, right? So they can kind of produce that many, but then they're not asymptotically totally geodesic. So I think it's sort of like a, yeah. So what I would say about this minimal surface entropy is that there should be a version of it where you're just counting like the primitive or the simple ones. I'd expect all the same theorems to be true. I think people are working on trying to prove things for that, but nobody has yet. But I think it's an interesting problem. And the difficulties there are more on the Kahn-Markovich side of
Mhm.
things. Of yeah, but yeah, thanks for the question. Okay, so yeah, and last couple minutes here. I guess I started a little late, but yeah, but I'll wrap this up pretty soon. Is I want to talk about yeah, just a quick application of this last theorem. Uh, right. So same steps as before. M is a closed hyperbolic clear manifold. And so the idea is, or the basic question here. So in recent years, there's been a lot of progress on the existence theory of minimal surfaces. Um, to the point where I think now like it kind of makes sense, or it's an interesting question to ask, like to what extent is a closed Riemannian manifold determined by the minimal surfaces that it contains? Right. And so I don't think very much of anything is known towards this question in general. But in the setting of closed geodesics, there is actually a decent amount known. And so kind of an analogy to that, I'm going to make the following definition, which is if you have some other metric on G, not necessarily the hyperbolic metric, the marked minimal surface spectrum is just the map phi sub G that given any homotopy class of pi1 injective minimals or pi1 injective surface in M is just going to be sending that homotopy class to the union of all Riemannian surfaces that is just kind of the union of all like the minimal surfaces that are homotopic to that pi1 injective surface. So a lot of the time you'd expect there to be a unique minimal surface. So this is just going to be like one Riemannian surface, but um, in general, it's going to be multiple. Right. So defined by just the set of all minimal surfaces that are homotopic to sigma, just as abstract Riemannian surfaces, right? So it's a lot of information, right? So I mean, the union of like Riemannian metrics on surfaces. Um, but remark that I'll make is that this is generalizing the Mark length spectrum. of a Riemannian manifold, which is mapping each non-trivial homotopy class of loop to the length of the unique geodesic in its homotopy class. Okay, and so a geodesic is just abstractly as a Riemannian manifold, it's just a circle, right? It's just a circle. And a circle is determined by its length up to isometry. And so that's why, yeah, I mean, if you try to like generalize this to higher dimensions, okay, maybe a more natural way to do this would be look at like the area of the minimal area um, of this homotopy class or of homotopy class of surface sigma, but um, I guess even kind of with like much more information than that, just knowing what like actually what the Riemannian metric is, I would say like yeah, nothing is known so far, and that's generalizing the Mark length spectrum. Okay, and so um, it turns out yeah, in the Mark length spectrum setting, I should have written this, but I forgot. Um, Bisson, Courtois, and Galot proved, for example, that a closed hyperbolic manifold is determined among all, say, like negatively curved manifolds, or like all negatively curved manifolds and that are diffeomorphic to it, by its Mark length spectrum, right? And so there's a lot of kind of results there. And so an analogy to that, we're uh, the question we're looking at is whether this marked minimal surface spectrum is enough to determine to determine the metric. Okay. And so we were able to prove something in this direction. So like a local version of this of that kind of a statement. Um, and so what we were able to prove, so with Yang Li and James Marshall Reber, is that there's a C2 neighborhood of the hyperbolic metric, so that if any other metric, so any metric in the neighborhood, if it has the same marked minimal surface spectrum as the hyperbolic metric, then it actually has to be isometric to the hyperbolic metric, right? So in that sense, the hyperbolic metric is determined by the minimal surfaces that it contains, at least in the C2 neighborhood. And but there's a little more information. You're kind of remembering not just the minimal surface, but like which uh, homotopy class it is. So it's not just the information of the minimal surfaces. We also need to know like which homotopy class of surfaces, yeah, is which Riemannian surface. Okay, but yeah, so that's a theorem, and then I just want to really quickly say how to prove this because it ends up like using scalar curvature, even though scalar curvature stuff, even though that's nowhere in the statement of the theorem. Um, and so that's like one reason I was yeah, I want to talk about this. So um the idea is that so there's this fact that minimal surfaces will be more negatively curved than the ambient space, right? It's basically from the Gauss equation and the minimal surface equation. And so in the hyperbolic metric, we have all these asymptotically totally geodesic minimal surfaces, right? And so for these, say you're just totally geodesic on the nose, well then your sectional curvatures are going to be the sectional curvature of the ambient tangent two plane and the ambient space is going to be the same as just the intrinsic curvature of your minimal surface if you're totally geodesic, or if you're almost totally geodesic, that will almost be true, right? So if we have a minimal surface in this other Riemannian metric M, um, then what that will mean if say that minimal surface is hyperbolic or almost hyperbolic, um, that will mean the sectional curvature through that tangent two plane to the minimal surface, it's going to have to be bigger than the intrinsic curvature of the minimal surface, which in turn is going to be -1 or very close to -1. And so it turns out, and there's some work here, and this is most of what I'm hiding in the sketch of the proof that I'm giving, um, that all these minimal surfaces are going to be dense inside the space of all tangent two planes to M, right? And so that turns out it's enough to read off all of the sectional curvatures, or kind of say the sectional curvatures have to be at least what they would be in the hyperbolic metric, right? And so here, okay, it's a sectional curvature lower bound. The higher dimensional versions of this, which is still work in progress, will actually be using scalar curvature lower bound. But here it's sectional curvature lower bound. But what I would say is like I mean, there's a lot of statements in Riemannian geometry, like the Laurel theorem, where the sectional curvature lower bound version of it, you actually need like the scalar curvature. Like the first proof of that is with the scalar curvature lower bound. So this is maybe a little like that, where um, yeah, we get a sectional curvature lower bound naturally, but really we have to kind of go to scalar curvature. Yeah, and so how do we finish the argument? Well, by the previous theorem, from the fact that we have the curvature lower bound, we get this upper bound in the minimal surface entropy with equality only if we're isometric. But we have the same exact minimal surfaces, right? So that means like whatever this minimal surface entropy is, which maybe you don't remember the definition, um, whatever it has to be the same as the hyperbolic metric if you have the same minimal surfaces as the hyperbolic metric, right? And so kind of combining the rigidity in the case of equality from the previous theorem with the fact that we have the same minimal surfaces and thus the minimal surface entropies have to be equal, well, that can only happen if G is isometric to the hyperbolic metric, right? So to summarize, we were able to get like the scalar curvature lower bound from the um, from knowledge of like what the minimal surfaces in a Riemannian manifold were, and just like the Gauss equation. And then using this like minimal surface entropy rigidity theorem, we were able to um, say that actually we could then kind of say that we had to be isometric with the hyperbolic metric. Okay, so sorry for going a little over, and I'll end my talk here. Thank you for listening.